Hello and welcome to session one of the 2025 MOSA Virtual Summit, Leveraging MOSA for Electronic Warfare and SIGINT Applications. My name is Dan Taylor, Technology Editor with Military Embedded Systems, the SOSA Special Edition, and the FACE Special Edition. I'm also moderator for today's event. To learn more about military embedded systems, please visit militaryembedded.com and check out our articles, blogs, and podcasts on military technology. Our speakers today are Ken Grobe, Director of Embedded Computing Architectures at Elma Electronic, and Nigel Forrester, Director of Strategies at Concurrent. Session one is sponsored by Elma Electronic and Concurrent. The MOSA Virtual Summit Platinum sponsor is Contron. The event is hosted by Military Embedded Systems Online and Open Systems Media. Before we begin, I have some housekeeping items. This and all Open Systems Media virtual events are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This session will consume about 40 to 45 minutes, leaving the remaining time for the question and answer session. Now let me show you around your viewing console. You'll find on the right-hand side an area where you can enter your questions in real time. We encourage you to ask questions throughout the session while the question is still fresh in your mind. We'll address as many questions as we can during the closing Q&A portion. If you have a question for a specific speaker, please note so at the beginning of your question, or I will offer the question to all of our speakers. If you have a question pertaining to the event operation itself, one of our technicians will get back to you during the session. Please note that as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the event with more information. Across the way on the left-hand side, there's a resources section, and that's where you'll find the slides being presented today and the MOSA ebook produced by our editorial team. Below that, you can view today's speaker information. I've got two more console features to share. Your console is customizable insofar as you're able to manipulate all of these widgets, Q&A, resources, and presenters for your ideal viewing experience. Expand them to get a closer look or close them to have the presentation window automatically resize around them. For maximum screen size, close them all and/or utilize the full screen control in the upper right-hand corner of the presentation window. To bring them back, simply click on the buttons in the bottom middle dock. We also have closed captioning capabilities in nearly a dozen languages. To enable this functionality, simply click on CC in the upper right-hand corner of the presentation window and select your language of choice from the drop-down menu. This session and event will be archived online at the same URL you used to join today's live session and will be available within 48 hours. Once up, it will be available for at least 1 year. Now, I'm pleased to turn it over to Nigel to get us started.
Thank you very much, Dan, and welcome everybody to what I hope is going to be a very informative and interesting session. So in preparation for the call today, I've really got three questions. Why would you want to base your C5ISR or electronic warfare SIGINT system on modular open standards architectures? And what does that mean, and how do you leverage the benefits? And hopefully I will show you a little bit of that throughout the presentation. So the first bit about the why is really, really basic, and that's, don't reinvent the wheel. So the whole concept of having modular open standards and some of the sub-standards, or MOSA is really a strategy, but there are a lot of actual standards underneath that concept, is that, if it exists in the outside world as a commercially available platform, it's often a good starting point. And we've had, over the last 5 years particularly, more and more customers come to us and say, oh, well, you've got hardware building blocks and application generating software, or application enabling software, I should probably say. We want to focus our efforts on the things that add more value, like our applications, and sometimes the integration. And that's great. But we also have customers who they're still struggling with the idea of the compromise there. And actually, it's fair to say that often you could do it better if you do it yourself. With a COTS product, there's going to be some compromise. Maybe it fulfills a percentage. Maybe it's 90, 95% of your requirements, but it's not 100%. But what I'm going to try and show is that that's still perhaps the best option. And I've got this slide because I think this really captures the ethos behind what this means for particularly defense applications that have very long life cycles. So often the total cost of ownership of that system or platform is something which we don't think about enough at the starting point. So it's really the biggest differentiator is that if you base your platform on MOSA based equipment, then the value proposition is that over the life cycle of that platform, the cost will be lower. I've got a straw man example because it is fair to say that it's not always the cheapest with initial purchase. Maybe your MOSA based platform costs you $100,000, whereas you could do it yourself for perhaps $80,000. However, the real saving comes throughout that program because over the 25-year or 30-year life cycle, you're going to need to do some tech refreshes. And every time you get a tech refresh cycle or you want to maintain that equipment, maybe it's a simple proposition that if you started with the right platform which had some flexibility into it, you might be able to upgrade that with maybe $40,000 worth of additional cost. Whereas if you're building it yourself, maybe that costs you another $80,000. So the pendulum starts to swing in the favor of that MOSA. And there are lots of other benefits, particularly with regard to things like serviceability, security, where by leveraging what is available on the open market, you get the best in class at a very reasonable cost. So what I wanted to do now is spend the rest of the time talking about, think about those signal integrity, signal processing and radar, C5ISR type applications. Many of them have a sort of a decomposed architecture, something like this. So if it's signal intelligence, you probably got some RF signals and there's some sort of receiver that converts those to a digital signal. And then you need to do some processing on that to come up with some sort of, you've got some clever algorithms that determines what devices you've got in the field, where they're situated, what frequencies they're broadcasting on, and other interesting things. And then you might want to collate that information and share it with various levels of security. Maybe you want to store it for post-processing. And then perhaps you want to take some action to jam or spoof those signals. So you want to actually transform them with some more signal processing and then radiate them back out through a transmitter. And if you look at that the other way around, maybe you've got a radar application where you're actually transmitting signals at the front end and then actually recovering those signals and working out what is actually happening where various platforms are situated in the theatre of operations. And all of those devices need very accurate timing and synchronization, and they all need to communicate ideally behind them. So the ideal here, and I know this is a gross simplification, but it sort of represents the type of flow that you might see in this type of application. The ideal is that you can select from a recipe of building blocks that work nicely together. That's the whole ethos behind MOSA. So let's look at some of those building blocks and why, before the sort of directives and things that we've got in our pocket today, why some of the technologies that we're using didn't work very well. So if I wind the clock back about 5 years, there was VPX and then Open VPX standards, which were the de facto form factor, if you like, and connectivity for all rugged defense kit. However, Open VPX particularly offered tremendous flexibility, well thought out standard, lots of work went into it, but having vendor defined user IO and the flexibility to implement a fabric of choice on the data plane meant that pretty much every single system was unique. And in many cases that required individual backplanes, it required individual connectivity. And what that really meant is that if I look at the sort of products that Concurrent had in the marketplace, for every generation of processor board, we probably defined a different set of user I/O. So we sort of shot ourselves in the foot because customers who are using generation A boards couldn't just remove a generation A board and plug in a generation B board because the backplane I/O was incompatible. So not a great sort of situation, but a lot has changed. And if I look around, I was listening to the keynote from Patrick Collier. He gave a great explanation, and John McHale also did, about the sort of top level directives that have been driven, particularly in the US, where we have this amazing directive around MOSA, and that you explicit mention of some of the underlying standards like SOSA, FACE, and Victory, which follows on a previous tri-service memo. And what that's done is it's really driven a massive change in attitudes and behaviors from the top down that vendors like Concurrent and Elma are trying to satisfy. So if I look around at the ecosystem today, and I pulled off this list from the completely open spreadsheet that's on the SOSA Open Group website, and this lists all of the products that are what are called aligned to the SOSA technical standard. So I'll talk a bit more about what I mean by alignment and conformance at the end, but currently there is the ethos of products being aligned. And from our own perspective, and we're obviously very strong in Intel-based processors, it's really great to see that not only Concurrent are playing in that field, but there are a lot of other vendors. So the snapshot I took showed there were 55 vendors today with compute-intensive processors. So these are things which have Xeon processors, lots of memory, probably lots of storage, high bandwidth, PCIe connection for local FPGAs or GPGPUs. They're really heavyweight processors. There's also another class of processors called IO intensive processors, which typically have slightly more lightweight processors, but have the benefit of a local XMC mezzanine for specific user I/O and a number of other benefits. And there are 36 of those today, so that's really good. There is also currently 17 switches. So the switches are the glue that connects all the other products together. And these typically have both control and data plane connections. Current state of the art is 10 gig control plane and 100 gig Ethernet data plane. And so that also drives the other payloads to have the same sort of connectivity. And the switch also acts as the gateway to the outside world. So you can see on this shot here, there's some connections on the front for a couple of fiber connections out to a sort of a WAN type connectivity. So lots of choice from a switch point of view. There is also some storage modules. And again, these are in some cases just a storage card. Some are front removable. So if you've got an application where you need to go out on a mission and then remove that data for post-mission analysis, you can easily slot in a new storage module there. And there are a number of timing and synchronization cards. So going back to the diagram, the simplified diagram I had of a SIGINT EW type system, the real key is that all of the elements of that system that are doing the signal processing need to be very accurately synchronized in time. And that's typically done through a GNSS connection. They come in on one of the RF connectors you can see on the sort of bottom left of the picture on the screen. And if that GNSS signal is spoofed or denied, the timing and synchronization card has some very intricate electronic devices, including a quantum timing device that actually keeps that time accurate to the best possible degree, and the ref clock and aux clock, as they're called, so that's a 1 hertz and a 25 to 100 megahertz signal, is then radially distributed across the backplane to all the other cards in the system. So there's a few timing cards. There are also lots of FPGA-based signal processing cards for things like tuners, software-defined radio, whatever as a user you want to put on there. That's see lots of capability there. And there are also, if I can click the right button, a lot of power supply units. So the great thing about some of the work that SOSA has done is that in the original VPX specifications, you could power your payload cards from either +5 or +12 volts. So when a integrator came to construct their system, they would very often have to specify a custom power supply that had X amount of watts on the 5-volt rail and X amount on the 12-volt rail. That's now gone away. So everything is +12 volts with a +3B3 aux power, which is used for the management interface underneath the that runs in the background, either out of band or inbound. And these power supplies now are effectively available off the shelf to suit the number of payloads and the wattage you've got in your system. And then dear to Ken Grove's heart, as he'll be speaking a bit later, is something that Elmer Electronics really have a huge influence on, and that is the things which connect all of these parts in the system. And that obviously Elmer do lots more besides backplanes, but the backplanes, we like to think of them as quite simple things, but actually there's a lot of technology in these backplanes, and the ability to buy a SOSA aligned backplane that will meet a number of different configurations is really interesting. So the overall message that I'm trying to give you is that there are lots of MOSA building blocks to suit most of your applications. These are all based on open standards though. So if you want to have a system which has 3 or 4 of the devices you get from the commercial market, there's nothing to stop you designing your own proprietary card. The reality is that if it exists on the open market, it's probably better to do that. So looking again at my very simplified diagram, how would we construct a system a bit like that? So I've got a slide here that shows more detail of the backplane. I'm not going to go into it in a lot of detail, but I just want to reiterate that if you go up from the bottom, you've got power and you've got a management interface that spans across every slot. You've then got the radial clock slot. So in this backplane, the third slot from the left is what's called the timing slot. And there are radial clock signals that go out from that timing card to every other card in the system. And above that, you've got the 2 control and then you've got 2 data plane connections. So the control plane is where your do this, do that type commands and some simplified reporting. Your data plane is where all your high-speed I/O signals between the various payloads happen. So control plane typically 10 gig, data plane typically 100 gig on the primary data plane. And then you'll see in blue at the near the top of the slide, you've got a couple of slots on the left and a couple on the right, which have the ability to make direct point-to-point PCI expansion plane connections between pairs of cards. And that's really useful if you want low latency, high deterministic, and high bandwidth connections between perhaps a CPU and a GPU, for example. So let's look at constructing a system with the proper view of the backplane. Start with the backplane. The slot at the right, that's where your PSU goes. And as I said, those are all standard now, easily obtainable at various different wattages. The switch slot in this backplane and most backplanes lives around the middle because the signals radiate either side of the switch. And the slot just to the left of the switch is where on this backplane the assured timing card goes. And so that really is your core system. So with those basic building blocks, you can build a load of different combinations. So as an example, maybe you're doing a simple signal intelligence type application where you have an external tuner device. You're bringing digital signals into your FPGA to do some signal processing. You've got a compute intensive processor next to that, linked perhaps by PCIe, and you're maybe looking at some signals and then doing some work on those and actually either sending results somewhere or perhaps doing some jamming. That same system can very easily be changed so that you might have an internal RF tuner. So you do all of the electronics within the box. So the great thing about the 3UVPX specification is it allows you to bring direct RF or optical signals into the backplane. And so you can actually bring your RF signals direct into a tuner in the board, and that might live in a separate slot like I've shown here, or it might live as a mezzanine on top of your signal processing board. Again, lots more options there. And perhaps if you're doing some C5ISR, you've got a more heavyweight signal processing application. You need perhaps a couple of FPGA boards to do that. In this particular example, I've got an IO intensive processor to collate that data, provide some intelligence, maybe display it, have some user inputs, and perhaps then assimilate that data and use a DDS service to spread that to the relevant people who need to know. And then I've also got another application here. We see this quite a bit, and I think Ken's got some examples around AI inferencing, where it's very easy within the same backplane to configure a compute-intensive processor with a NVIDIA-based GPGPU for AI acceleration. So there is lots of options there, including this one here, which has more compute capability. So in summary, lots of things are possible there, and the really key to it is the fact that the underlying standards under that MOSA strategy have led us to have a level of interoperability. And we've seen many cases now where customers have taken the best in breed computer, FPGA, switch, power supply, backplane, and they've been able to construct very interesting and exciting systems in a very simple way. However, there is more to do. So very recently, we've been at my US colleagues have been at a SOSA interop event, which is a private event where a lot of the vendors have come together to make sure that in a confidential way, we do a really good job of making our devices interop with each other. And in future, if you're listening to the keynote, there's quite a lot of discussion about the SOSA conformance program. At some point in the not too distant future, we'll be taking that a massive step forward, where instead of being able to claim that our products are SOSA aligned, so it's sort of a best effort helped with these interop events, we will actually have gone through a formal conformance program, and we will be able to demonstrate that our products are absolutely where they should be, and give you as a user the best possible experience. And with that, I'd like to turn over to Ken Grobe to give you a lot more detail on their product.
Thank you, Nigel. Good afternoon, everybody. My name's Ken Grobe. I'm Director of Embedded Technology with Elm Electronics. Great overview from Nigel about the building blocks and how systems can be put together. So, as Nigel introduced, MOSA, sometimes we think of it as modular standards, but actually it's a modular open system approach. And this is an approach directed by the tri-service memo that's been updated twice, as Nigel pointed out, that is helping us to standardize our interface and deliver technology more rapidly at better cost as systems are implemented. So moving on, Today, I'd like to cover where MOSA is being applied, some of the challenges that have driven the open standards or are driving the open standards, and why, how SOSA affects the architecture of the systems and the adoptive standards, a little bit about development and deployment. You have to start somewhere when you're putting a system together, and then ultimately it needs to lead towards a deployment platform which is ruggedized. In Nigel's RF chain, he is explaining and showing the architecture for RF systems. Wanted to talk a little bit about MORA, which is one of the standards referenced by SOSA and CMOSS to put systems together that use RF elements. Also touch on chassis and system management, which is a capability required by SOSA for managing systems, and chassis management for managing PICs and things that are in the system. Hardware architecture, touch on that a little bit about AI and how you can be enabled to put elements of the system together for AI applications. A brief look at a CMOSS case study, and then a few of the ecosystem building blocks that are available. So where will MOSA be used? It's being mandated. Obviously, it can be used across the tri-services as mandated by the DoD. And what we're seeing is that it'll be used in many places, at embedded systems at the edge, in sensors, since SOSA stands for Sensor Open System Architecture. These reference models are being developed to support different modalities of use. Modalities like signal intelligence, communications, EW, and ISR, to name a few. This is not the only ones, but these are some of the primary modalities. So if we look at challenges and take a look inside a vehicle and look at what needs to get done, we see on the right kind of a messy picture of a bunch of boxes in a vehicle with interconnecting cables. And what we see is as the warfighters' use cases change and the need from the DoD evolves, what we need to do is develop mission capabilities that span these different modalities, including communications, EW, radar, and SIGINT. And sometimes one would want to modularize this capability and be able to sort of mix and match it within a chassis, which really can't be done today. Although as we go forward, multiple modality systems will be possible, which gives us a way to address size, weight, and power and the space claims within the platforms. So we need to do this because threat posture changes in the world, and it requires us to make new equipment, modernize that hardware, and get it out to the warfighter in a timely manner. Also, when you look at this, you've got a complexity of different types of, let's say, functions that need to be maintained. You have training around that, and you have upgrades. So where standardization can take place, it helps reduce this cognitive load on the user and make it easier to actually implement it and maintain the systems. Sorry, my button is a little bit stuck. Further, if we look at the space claim, picture on the right shows a complement of systems that will be implemented in the vehicle. What's occurred over time is that without standardizations being driven down from the top, one tends to get into an environment where you have stovepipe systems, where there's expertise from certain suppliers around quite good hardware that gets implemented, but it becomes sort of implemented up a vertical. So interoperability across that equipment may be more difficult. Leaving industry develop different components that could modernize the equipment is not really possible. And then you run into size issues where you've got a constraint in a platform where you only have so much space. So this leads you to competition within the platform where you may not get the capability that you need because you don't have any room to put it anymore. So these are things that are sort of pressing on the different corners of the solution and the implementation that add complexity, and then that can lead to additional cost. So one says, what is a better way that we can achieve these things? And this is the goal of the modular open system approach. So if we think about deployment and development, what we need to do is start on the left with a development capability and then move that capability to the right to a deployment environment. So this is what we're reflecting in this diagram. Around that, we sort of have these vertical technologies that are pointed to by the standards that let us address different elements of the system. So the top one is something called MORA, or Modular Open Radio Architecture. The middle is a stack of technologies that would be available from NVIDIA that would help folks use this technology to implement AI capabilities. And at the bottom, what we have is a set of architectural standards that implement an architectural called systems and chassis management that allow one to interface with the system and to also control it. So if we look at this, and Nigel gave us a spoke that showed different activities in his presentation. Here, we're showing technologies and standards in a stack and how those standards and implemented capabilities can form a sort of hierarchy to get you to the overall sensor capability. At the bottom, what we have is a standard called OpenVPX that describes the hardware. And the next thing that one would need to do is take that OpenVPX standard and manifest some sort of environment that allows you to develop. And that would be done in the gold block with development systems. And of course, these would be produced by multiple manufacturers. I'm looking today at what Elma is offering to the market. So to the left, we have that black box. It's a compact frame that includes a backplane and a power supply. It also includes a chassis manager that gives us the capability to develop and combine PICs into a system. On top of that, other technologies that could be incorporated would be available from companies like NVIDIA with implementations in the marketplace of GPGPUs that allow you to apply this to form AI capability. And sitting on top of that is something called MORA, which is an architecture for RF. And along with that, there's tools and reference platforms that can enable that capability within a system to handle the RF. Lastly, you get to what is really the bottom line, the customer application and the sensor modality, where tons of work is being done in that blue block to implement the overall system capability, which is the end game. So taking a look at these quickly, one by one, we see what SOSA has done. There's a lot of talk about the hardware aspects of SOSA in normalizing the hardware, which is completely necessary. But SOSA is doing other things that doesn't usually get as discussed as much, where we see work being done in the software infrastructure to promote interoperability and portability. One thing SOSA does is implement the runtime environment, or define the runtime environment, I should say. And it's supporting things like FACE OSS, which is an example of reuse, where FACE has been around prior to SOSA, which provides an environment for operating a system or building a system. It also defines containers, which allow one to abstract software modules to promote interoperability through container definitions like Docker and Kubernetes. Further, it gives us a recipe for the virtual machine architecture that should be used and guidance on how to implement that. All of this helps to promote interoperability. Then when we looked at next step, SOSA also points to capabilities called system and task management, where the system manager is responsible for managing modules and infrastructure within a SOSA sensor. This breaks down into a bunch of APIs that need to be implemented. And it's also related to another function called task management, which is what actually coordinates the operations of the sensor. Lastly, we've got Modular Open Radio Architecture, which is a standard that's pointed to by CMOSS, CMOSS being C5ISR Modular Open Suite of Standards. And this defines how the signal layers should be implemented, and it's actually a requirement for things that will be CMOSS aligned or ultimately CMOSS compliant. So looking at challenges again, to make products be able to be developed that are interoperable and to develop them quickly, we need to have a definition that is accomplished through MORA. Again, MORA is Modular Open Radio Architecture. And what it does is decouple the RF hardware and signal processing chains. It actually decomposes it into components that are well-defined. So manufacturers have a common recipe to implement these capabilities. And it allows you to grow on existing efforts and to take that forward into new designs. So we look at the building blocks. What we see is elements like a software-defined radio that's picking up its data from the high-speed data bus, or what's called the MORA low latency bus, and then communications for control through something called the VDB, or Victory Data Bus. And as we go around the buses that implement the data flows within the system, what we also see is other functionality, a processor or a mission processor, and that implements parts of the MORA architecture, radio heads and antennas and power amplifiers, and below that RF distribution devices. So MORA decomposes the radio system into high-level components that enable sharing. And when you're considering software-defined radios, what's needed there is flexibility to run things like different waveforms for voice communications and EW. MORA lets all these things happen in a modular way, and it allows one to be able to build on work and then potentially reuse that work to keep technology refresh, let's say, possible, making it faster, that allows one to innovate new capabilities faster. If we look at how that decomposes, a MORA ready system that has elements of the MORA standard already implemented is possible. And this shows an example of what we call a MORA ready development platform. In this case, we've got a processor by Abaco for mission computing. This could also be a processor from Concurrent that operates in a similar way. We support both. We have a switch, and then we have a transceiver. The transceiver implements or looks like a MORA device, which is actually a software-defined radio, and it communicates over Ethernet, both in the control and data planes. So we have MORA signal domains taking place in the RF receiver. We have a single board computer that implements MORA processing as a processor resource. And we have a high-speed switch that does the data flow networking that's required between devices within a particular system. To the right, what we've got is profiles. And as Nigel mentioned before, these profiles were not defined or standardized, but made it practically impossible to have interoperability because the I/O mapping would be different. Today, that mapping is specified. So manufacturers need to use these profiles that are shown. The one in the middle here is the one for PNT. The one to the right is the switch. The one to the left of the first slot is the payload profile, and then the I/O-SBC profile. This allows manufacturers to make interoperable PICs and then ultimately allow them to be ported to the MORA standard to be able to handle RF. So lastly, how do you attack the software? Now the ecosystem is addressing ports to MORA with tool sets from a company we are partnered with called Science Innovations. What we're doing here is taking the different elements of a MORA tool suite and utilizing that to integrate it into off-the-shelf PICs to make a system MORA ready. The tools that you would get would be MORA Explorer, which is like a terminal that allows you to interface with MORA functionality in a system to be able to give it controls and to also to be able to do things like review and display information that's in the MORA, let's say, API. Secondly, one needs to manage the MORA resources through something called the MORA signal resource profile. And this is done with a tool called an MSRP generator. This allows you to describe an RF device and to give it a profile so then that it can be then communicated with in the context of using MORA. In the middle on the right side, we see a block that's equivalent to the SDR. And there are certain functions that must be put into that. And these are implemented with what we call Helix Core and Helix Client Core to implement and stand up the MORA capability within the device. So these tools across the board then allow one to quickly leverage existing software to implement MORA capability within a system that must use RF devices. So now I'd like to show a quick video that shows a little bit more about how this works. And I think we'll tee that up from Marvin. So you just keep this moving. Let me touch briefly then on two other technologies that are in our stack. AI application and making systems, say, capable to use AI elements, and that would be comprised of GPGPUs and CPUs, requires an architecture that lets these high-speed communications take place. As Nigel mentioned before, what we've got is the need for PCIe to take place across the expansion plane. And what we can actually do is put multiple instances of GPGPUs in a single system if needed. So to accomplish that, we need to be able to connect a processor, which has an Intel SBC, or is implemented with an Intel SBC, and then connect that up to GPGPUs. Here we're showing two instances of that through standard profiles that are available in OpenVPX and defined within the SOSA specification. If you need a higher performance implementation, you need to have a wider data path. And to do that, there's a secondary slot profile that expands the width of the data path to by 16 between two payload slots that allows one to use the widest possible communications pipe between the GPGPU and the processor. So what we're doing at ELMA is putting all that capability into a backplane that we call backplane suited for AI development or AI ready. And what we're showing in these two slots are standard payload profiles that are implemented connected to an IO SBC, and then the possibility to add a compute-intensive SBC along with a high bandwidth GPGPU that uses the wider connection. This may be manifested in a different configuration in the ultimate deployment platform, but this allows one to quickly be able to mix and match devices like RF devices against GPGPUs and CPUs against GPGPUs for compute-intensive applications to perform development. Some of the processors or GPGPUs rather that you could get from our partner ISO include the Ampere GPGPU with wide input. This is up to by 16. It can be used by 4 by 8 or by 16. and then also system on module capable GPGPUs from the Orin, AGX Orin system on module that implements the Ampere architecture and an ARM processor cores within that device. So both of these types of devices can be plugged into slots that are described by standard profiles and then stood up against CPUs that can drive them. So the next component of technology I'd like to talk about is system and chassis management implementation and the tools that can be used to develop that. That's pointed to by this architectural diagram that's found in the SOSA specification. In this, we've got two types of interfaces, two types of interfaces, the in-band and the out-of-band. But before we get to that, we look again at standardization that's being promoted by SOSA for the RTE being the runtime environment. And here, different configurations of the RTEs are described. The one that's interesting today that's being looked at quite a bit is container RTE that allows us to modularize software using container architecture in the runtime environment. Further, you might need to use virtual machines, and the virtual machine RTE is also defined within SOSA, including examples of the hypervisor. What this leads to is more like an app store sort of concept around SOSA software, where software will be modular and much easier to operate out of the box than if these things are left open and not defined. So this helps with interoperability and portability. When we look at system management, the specification defines APIs for both the in-band and the out-of-band. The out-of-band interface communicates with the SOSA hardware or SOSA aligned hardware that's within the system, and it talks over something called IPMB. The in-band typically talks over network interfaces, and there's a host of functions that are defined in the in-band interface. This is a RESTful interface that communicates over a network from the hardware elements to the system manager, and also between the system modules or the aligned software modules. If we break this down, the system management is implemented across a bunch of interactions, and we see them defined in this chart. We have interactions for the system manager, the chassis manager, interactions for the PICs, which in many cases are processors or they're the plug-in cards that have other hardware functionality, and then the runtime environment. So a number of APIs. What this affords is the ability to modularize the software and to offer building blocks that can be reused, which is beginning to occur. So in this way, one can implement the agents and the clients and server software modules that are necessary to implement system management. As an example of that, Alma has been working with Science Innovations to develop a system manager user interface that does things like show sensor status, sensor state and mode, and bit configuration and use, so you can be able to control these things. As time goes on, more of the software will become available and supported by the ecosystem, and it's Alma's goal to be able to release an initial product within the year. So wrapping up with a case study, over the last 5 years, actually more than that, the Army's been working on adopting standards that will get them to this point, which is called the CMOSS mounted form factor. Alma has participated in this. We've participated in it with other partners in the ecosystem like Concurrent to develop a capability, in this case a chassis that's aligned with SAVE, that implements the standards that are prescribed by the Army if one would be compliant with CMOSS. What this does is provide a standardized space claim for the vehicle and a platform where people can use or developers can make system architecture like the ones that we talked about in the beginning and are a topic of this presentation, including EW, communications, mission computing, etc., and to be able to quickly get that into the field. CMFF will be implemented by multiple manufacturers to give a choice and to help manage the cost. So there will be a number of folks in the ecosystem will actually build to this standard. So last couple slides, looking at the architecture of a system that uses a SDR and an SBC. The items in blue show where MORA is utilized within an RF device. And over here, what we're looking at is where system management would be used in a processor. In the middle, we're looking at the switch and the data flows between them. And at the bottom, where we have chassis management implemented in the system to provide functions or provide the capability to provide chassis-related functions. So building blocks to implement these capabilities are now becoming available, as Nigel pointed out, with a great wrap-up from available hardware. We've got multiple people making development systems, deployment chassis, PNT cards, network switches, transceivers and SDRs, and a number of folks making power supplies. Recently at the Plug Fest, we had a number of the suppliers building these things available, plugging and playing them within chassis that were available at the Plug Fest to make sure that they interoperate. And I think there were 4, maybe 5 different companies making power supplies that were plugging them in and out and seeing good results during that event. So in wrapping up, system packaging for deployable solutions are the ultimate goal from Elma's point of view. We have 2 systems that are aligned to SOSA and CMOSS today that implement the SAVE standard, and the top one, which is a CMFF system that's 7 slots. And below that, we have a top loads 6 or 7 slot solution that implements connectorization that's defined by SOSA, addressing chassis management and an open platform. So that's all I have. Thank you for being able to speak about the MOSA approach today, and I'll turn this back over to Dan.
All right, thank you, Ken, and thank you, Nigel, as well, for your time and for those overviews. We've got a few minutes here for questions. So I'll start with you, Nigel. Can you talk about how the adoption of MOSA speeds time to deployment?
Yeah, I'll give you a sort of a partial view. So obviously, adoption of these modular open solutions architecture building blocks that we've just talked about can dramatically speed up the front end of that process, you know, getting you to a system that does what you want to do to load your application. It can dramatically help in the technology transitions, but there's still a lot of other steps between, you know, the development and deployment, a lot of qualification. So there's a significant potential time saving, but every application, every program will benefit to a different level. So I can't give you it'll definitely shave a year off your development schedule. It really depends on what you're doing, but there is a lot of scope for time saving.
Okay. Ken, can you talk about how system management software, where do you run it? Is there system management software available, and where do you run it?
Yeah, so good question. System management software can be run at multiple levels. It could be run within a box, say on the iOSBC, or it can be run because it's connected via a network. It can be run external to the box. So it will probably be done in multiple places, depending on the particular implementation, but it is sort of modular in a sense that you can locate it in different, let's say in the places where it's needed. Secondly, yes, we'll see system management software starting to emerge, I think, this year. We're focusing on the chassis manager related needs in the RESTful API and also in the system manager UI. And we should see that later on, probably by the second quarter.
Great, thank you. And a question for you, Nigel, referencing, I think, a spreadsheet you mentioned earlier where it helped the individual understand how many SOSA aligned cards were available. The question was, would it be doable to include the slot profile for each card in the list?
Yeah, so that's a great bit of feedback. So that relates to the spreadsheet that details the SOSA aligned payloads that's available for anybody to download from the Open SOSA Group website. Absolutely, we'll take that feedback and we will put that in the SOSA outreach committee and we'll look at adopting that. I think it's a great idea.
Great, thank you. And Ken, or what SBCs would support the AI backplanes?
So Nigel pointed out there's quite a few, but we've been focusing and doing a lot of our interoperability testing with single board computers that are available from Concurrent. So when you look at, there's two profiles. You can have the compute intensive primary profile and the secondary profile. And Concurrent's offering products that address both of them. And one will give you by 4 and by 8, and the other will give you up to by 16 to be able to make this implementation. When you're thinking about what you want out of that, as you want to say drive towards the apex side of that, you're looking for multi-core, high performance, lots of memory. And then that will be connected either to the by 8 or by 16 interfaces to do the HPEC AI sort of things, like if you're running an inference model and you need higher processing capability. The task is lighter weight. We could use IO SBCs that are available from Concurrent and implement the IO SBC to GPGPU link with by 4 connectivity. And we've been doing that over the last couple of years. What we've been building up to is getting to the by 16, where we can really do that heavy horsepower stuff. And I think this year we'll be in a position to start showing that capability.
Okay, great. I think we have time for one more question. So Nigel, I'll leave it with you. Technology transitions sound good in principle, but are they really practical?
Yeah, let me give you a really good use case. So we have an existing customer who took a small handful of one of our early SOSA aligned compute intense profile boards to do their initial development work. They were happy with that product, but it didn't meet their weight constraints. Nor did it meet the upper temperature limit that they needed for their system. The original card was plus 70 degrees C max card edge. They wanted an 85 degrees C card edge implementation. So we offered up a new product last year that the customer was confident enough to do a technology transition that they went straight to their low rate of production. So they went from a small handful of the previous generation cards to 180 of the next generation cards with no impact to their application capability. So that's just one example. There are many that will help with that technology transition.
Great. Well, that brings us right to our time limit for today. Sorry, we could not get to all of your questions. Someone may get back to you after the event with more information. I would like to thank Ken and Nigel for speaking today, and Elma Electronic and Concurrent for sponsoring the session, and Contron for being the Summit Platinum sponsor. This and all Open Systems Media virtual events are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This event will be archived online today at the same URL you used to join today's live session, as well as the URL shown on your screen, and will be available for at least 1 year. Please be sure to attend our next session, MOSA at the Edge across multiple domains, starting at 1 p.m. EST. Goodbye, everyone.